Hi, I'm Professor Goins. In this video, I'm going to continue the discussion on surface integrals. In the part one of this sequence, what I did is introduce the geometric idea of what a surface integral was, how to set up by changing the limits of integration, which would be the region of integration, the differential, and the integrand in terms of just x and y. In other words, eliminating the z and eliminating the d sigma, converting that into information with just the x and the y variable. At the end of that video, I started this example right here and I got interrupted, so I ended up turning it off and just kind of deleting that last part of it, so I wanted to redo it. So I'll do this example and then I'll do another example after that. Okay, so in order to compute this integral over s of x, y, z d sigma, where x, y, z is the function that I'm looking at, d sigma is going to be a surface differential on this portion of the cylinder, and s, again, is that exact region where I've got the x value goes from 0 to the radius of that cylinder, which would be 2, and let's say this goes to, I think I said 3, but that's what we'll go out to. Okay, well, remember that we have to change the region of integration, the integrand, and the differential. So in this case, the surface S is going to get translated to the region D, which lies in the XY plane, and the region D is going to be the shadow projected down from the surface down onto the XY plane. And again, just to add a little dimension to that. Okay, so that looks like the region D consists of x goes from 0 to 2, and then y goes from 0 to 3. So we have constant limits of integration. And then for the variable z within the integrand, we are going to use the equation of the surface. So notice if I solve for that, I would get, if I subtract x squared, take the square root, and then since this is above the xy plane, we're going to take the positive radical. So in other words, z is going to be equal to the square root of 4 minus x squared. Okay, and the last thing to change is the differential. And the differential in this case, remember the formula, if you watch part one of this video sequence, this is the square root of, make sure that's on the screen there. Let me write that a little bit lower. So let's put it about right here. So let's say d sigma was the square root of take the partial derivative of f with respect to x and square it. Then I add the partial of f with respect to y, square that, and then it's plus 1. And then I have an area differential dA, which again was either dx dy or dy dx, depending on the format or the structure of your region of integration in the plane. All right, so let's go ahead and evaluate this. Well, the partial of f with respect to x, so f again is this function here, the function z. So I take the partial of that with respect to x, and we get the following. So that would be 1/2 4 minus x squared to the negative 1/2, and then a factor of negative 2x comes out front, or comes outside, and then I square that plus partial of f with respect to y. This is independent of y, so the partial of f with respect to y would be 0, and then I have plus 1. dA. All right. Inside, underneath the square, I would have a 1/2 and a 2, so those would cancel. And then I would have a square, so that negative is going to become positive. This x would become x squared. This negative exponent will get flipped to the bottom, making that a positive 1/2. But then 1/2 squared would be exponent of 1, so therefore you would get the following. So again, this negative exponent would flip to the bottom to make it a square root, but then I'm squaring it, so the square root cancels, leaving just a 4 minus x squared on the bottom. This x becomes x squared, that goes on top, and then negative becomes positive, 2 and the 1/2 cancel, and then I still have the plus 1 at the end here. All right, so now I've got my new region of integration. I've got the change of variables, or the substitution to make my integrand just in terms of x's and y's, and then I have my new differential. So here's the integral that we are going to then compute. So I start with the surface integral, double integral over s of x, y, z d sigma is equal to, since these are constant limits of integration, it doesn't matter if I integrate with respect to x or y first. So since it doesn't matter, let's do 0 to 2 and then integral 0 to 3. So that'd be with respect to y first and then x second. And then it's x, y, z. So I'd have x, y, and then z was the square root of 4 minus x squared. And then it's d sigma. D sigma is this radical right here times dA. So that'd be the square root of And then in order to integrate this, what I'm going to do, since these are both square roots, I'm going to multiply what's underneath. Okay, so that will give me Now, to simplify that radical, here's what I'm going to do. Rather than, because I've got 2 terms here and 2 terms here, rather than foiling it, I'm going to keep this as a single term, and I'm going to distribute that through. So I'm going to take this 4 minus x squared, and I will distribute that to this term right here, and then I will distribute that to the plus 1. Okay, so let's see what that gives us. I'm still on screen. Okay, so this is integral 0 to 2, integral 0 to 3 of xy square root. Okay, when I take 4 minus x squared and I distribute that to this first fraction here, notice the 4 minus x squareds are going to cancel, leaving just an x squared. Then I take 4 minus x squared and I multiply that by 1. That would give me plus 4 minus x squared dA. Under the radical, notice I've got an x squared and a minus x squared. So that and that would cancel, leaving just the square root of 4, which gives me a 2. So I'd have a 2 would be a factor of my integrand, so what I'll do is I'll bring that outside of the integral. So that would give me the following. And in this case, remember dA is an area differential in the plane, xy plane, and since these are constant limits of integration, I can integrate in either order. We chose to integrate with respect to y first, so therefore this would be dy dx. Okay. So then we compute that double integral. So then this gives twice integral 0 to 2. And then now I'm going to take the antiderivative of xy with respect to y, which gives me xy squared over 2. And we're evaluating from y is equal to 0 to 3 dx. Okay. This denominator of 2 here, I can bring that out front, so that 2 over 2, 0 to 2. So then I plug 3 in, so that would give me x times 3 squared minus x times 0 squared dx. 2 over 2 is 1, so that's integral from 0 to 2 of 9x dx. And then now it's an integral, just a single integral. So antiderivative of 9x would be 9x squared over 2 from x equal to 0 to 2, which gives me 9 times 2 squared over 2 minus 9 times 0 squared over 2. Of course, that term is 0. 2 squared over 2 would leave me one factor, 2 on the top. 9 and 2 would be 18. So the surface integral has value 18. All right, let's set up and do one more example. So let's say in this case, my surface S is given by the plane z equals 3. And let's say the plane goes from say x goes from 0 to 3 and y goes from 0 to 4. And what we're going to do is evaluate a double integral over that surface. All right, let's evaluate okay, so the double integral over S of x plus yz d sigma. So the surface S gets projected down to the surface D, or so the plane region D. And notice in this case, the plane z equal to 3 is parallel to the xy plane. So when I project that down, I get that plane region in the xy plane with the same limits of integration. X goes 0 to 3 and y goes 0 to 4. Okay. Within the integrand, I'm going to change the z using the equation z equals 3. So the equation of that surface is equal to 3. So therefore, again, I've got z is equal to 3. And then finally, we've got our change of differentials. So d sigma is the square root of, well, I take the partial derivative of the equation of the surface, I take the partial of this with respect to x, which is 0, so I've got 0 squared, plus the partial derivative with respect to y, which would be 0 squared, plus 1 dA. Okay, so this is essentially a trivial surface because it just boils down to essentially integrating over the same limits of integration as the original surface with a change of differential where this is just 1, right? My sort of correction factor for the differential is just 1. So d sigma equals dA. And that again will only happen when the equation of the surface S is parallel to the xy plane, okay? So then my double integral becomes the following. I'm going to get the integral from 0 to 3, integral 0 to 4 of x plus yz, so x plus y times, well again, z equals 3, so that's y times 3, and then this is with respect to y, so that'd be dy dx. Okay. All right, so antiderivative with respect to y, so integral 0 to 3, and then that'd be xy plus 3y squared over 2. Evaluate from y is equal to 0 to 4, and then dx. Plug in the upper limit of integration. This would give you integral 0 to 3, 4x plus, so if I plug 4 in, that'd be 4 squared, which is 16. 16 over 2 would be 8, and then 3 times 8 would be 24, and then dx. Okay, antiderivative of 4x would be 2x squared. So 2x squared plus 24x evaluated from 0 to 3. So that would be 2 times 9, 24 and 3. So that would be 18 plus, let's see, 24 and 3, so it'd be 76. So that would be 94.